All right. Today, we're going to dive into the story of one of the most brilliant minds in genetics, someone who, for decades, was almost completely overlooked.
I mean, that's a pretty bold statement, right? It kind of hints at this hidden history, you know? A scientific giant whose work literally shaped how we understand life itself. But her name? Most of us have probably never even heard it. So who was she? And what did she figure out that was so far ahead of its time? Well, that's exactly what we're about to get into. Her name was Barbara McClintock, and her big discovery? It was so radical, so out there, that the scientific world just refused to believe it for decades.
Okay, so to really get her work, you first have to understand the person. And let me tell you, Barbara McClintock was a force of nature right from the get-go.
So, born back in 1902, she was this fiercely independent kid. And when she discovered her love for science in high school, it wasn't just some phase. Nope. It became her life's calling, and that path led her straight to Cornell University's botany department. And just look at this timeline. I mean, wow, she just blazed through her degrees at Cornell, a bachelor's in 23, master's in 25, and a PhD by 1927. We're talking a PhD just 4 years after her bachelor's. It was obvious she was brilliant, and yeah, people were definitely starting to take notice.
So let's talk about cracking the chromosome code. You know, early in her career, she wasn't an outsider at all. In fact, she made this huge breakthrough that would become like a cornerstone of modern genetics.
And this is what's so incredible. By 1931, other folks had theorized that genes could trade places, but Barbara McClintock, she was the first person to actually see it happen. Using corn, or maize, she figured out a way to watch under a microscope as chromosomes physically tangled up and swapped pieces. This whole process is called crossing over, and it was the very first visual proof that genes were real physical things sitting right there on the chromosomes.
She was basically inventing a whole new field here. Cytogenetics. It's this mashup of studying cells, cytology, and the principles of genetics. And this work? This is what first made her famous. She was a star in the scientific community.
But that work, the stuff everyone accepted, that was just the beginning. Her most revolutionary ideas, well, they started with a really simple but deep observation she made in the cornfields.
Yeah, the puzzle of the speckled corn. I love this description, as if they'd lost a paintball tournament. She's looking at these corn kernels with all these weird speckles and splotches of color, and it just didn't fit the neat and tidy rules of genetics that everyone knew. The go-to theory was, oh, it's just random mutation. But that didn't sit right with her. The patterns seemed, well, they seemed too controlled for that.
So after years and years of super careful breeding and observation, she came up with an idea that was completely out of left field, but it was an idea that could explain that speckled corn.
Here's her radical theory. Basically, genes aren't stuck in one place. She proposed that certain bits of genetic material could physically move or jump along a chromosome. So let's break it down. Step 1, a genetic element jumps from its spot. Step 2, it lands smack in the middle of a gene that produces color. And step 3, that color gene gets turned off, or at least its volume gets turned down. That's how you get a colorless spot. But then, if that element jumps out again, the color gene can switch back on. This explained the speckles perfectly.
Yeah. Today, we call these things transposable elements, or more casually, jumping genes. But McClintock, she called them controlling elements. And that name is so important. She didn't just see them as things that moved around. She saw them as regulators. They were in control.
And that's the key takeaway here. This was about so much more than just corn kernels. Think about it. If genes could be switched on and off, it could finally explain one of biology's biggest mysteries. How does a complex organism with the exact same set of genes in every cell develop all these different parts, like skin cells, muscle cells, nerve cells? This was the discovery of genetic regulation.
So she'd found the answer. She had this huge, groundbreaking idea. But when she tried to tell the world about it, well, the world just wasn't ready to listen. Not even close.
You really have to put yourself in the mindset of the 1950s. The established thinking, the dogma, was that genes were static. They were like fixed beads on a string, an unchanging blueprint. And here comes McClintock's theory saying genes are dynamic, they're mobile, they jump around. To her peers, that sounded like pure chaos. It just didn't make any sense.
And the reaction was, well, it was bad. Her discovery was either flat out ignored or, even worse, it was ridiculed. Her colleagues were confused, some were openly dismissive. The pushback was so intense that by 1953, she just stopped publishing her research on it. She felt completely alienated. Now, she never stopped doing the research, but she stopped sharing it with the world.
Just let that sink in. 35. For 35 years, her most important discovery was just sitting there on the fringes of science. That's how long she had to wait from when she first published her paper for the rest of the world, and yeah, the Nobel Committee, to finally catch up to where she'd been all along.
But here's the thing about science. Eventually, it does catch up. Technology got better, new evidence started popping up, and slowly but surely, the world started to realize, oh wait, she was right. She was right all along.
And you can see that shift happening right here. In the 60s, a couple of French scientists described gene regulation in bacteria, and it was like a light bulb went on for the whole scientific community. They realized McClintock's work was valid. And then the honors just started pouring in. The National Medal of Science in '71, she was the first recipient of a MacArthur Genius Grant in '81, and then the big one, the 1983 Nobel Prize in Physiology or Medicine.
And get this, she remains the only woman to receive an unshared Nobel Prize in that category. Not just a winner, but the only woman to win it all by herself. That just speaks volumes about how singular and groundbreaking her work really was.
But here's one last, kind of fascinating twist to the story. For McClintock, getting that Nobel Prize, it was a little bittersweet. It wasn't the simple happy ending you might think.
So she was grateful, of course, but she always felt that the prize was given for the what, the transposable elements, the jumping genes themselves. But what she thought was way more important was the why, the whole concept of genetic regulation. She felt like they gave her the prize for the cool trick, not for the profound biological principle she had actually uncovered.
Her whole story is just such a powerful reminder, that scientific truth isn't some popularity contest. It's not about consensus. And the most groundbreaking ideas, they often face the most resistance. It really makes you wonder, doesn't it? What other geniuses are out there right now with ideas that seem radical today that we're just ignoring?